Here are some guidelines for our lab number 3 on plate tectonics. There are two things that you need to print out to go along with the lab, and they're shown here under week 4. There's a base map that you might have printed last week to go along with your lectures, but you still want a fresh copy of that, and then a supplemental instruction page as well. So make sure you're aware of those when you do this lab. The first part, this table here, asks you to compare continental and oceanic crust. Now, we're not talking about lithosphere, we're talking about crust. And most of these we've talked about: density, thickness, location. Some of these you can find on the internet. But one thing that we definitely have not talked about is composition, and we will talk about that when we talk about rocks. But I'll go ahead and give you the answer to that. The continental rocks overall are similar to a granite, and the term we use for the rocks on the continent is felsic. It means they're rich in feldspar and silica. The ocean crust rocks are mostly a rock type called basalt, and those are mafic, which are rich in iron and magnesium. So you can put those answers in. Don't worry about understanding them at this point. You don't need to know this for exam number 1. It just happens to be on this chart. But I think the rest of this you can fill out just fine. Then it asks you to do some sketches that include lithosphere and asthenosphere. I've done this in lecture when we talked about continental drift, and we also did something very similar in the last lab. So I think you should be able to do this without any problem and briefly answer these questions. Now, number 2 is the part that you need the map for. On the map, it asks you to locate each of these plates and lightly shade them and neatly label them. So here's the map, and actually all the plates are already labeled except one that I have labeled here called the Juan de Fuca plate. It's this little plate right here, right off the coast of Oregon and Washington. So that's already been labeled for you. And then it says shade the plates. So that's my version of shading 2 of the plates, the Cocos plate and the Nazca plate. But you want to shade the whole map so that the different plates kind of jump out at you. And you should probably do a nicer job coloring than what I did. Number 3 says color the plate boundaries according to their type. So for divergent boundaries, you're going to use a red color. And I've highlighted just one divergent boundary on this map, which is the Mid-Atlantic Ridge. And it's offset, so you want to make sure you're true to where the offsets are. So just like down here, there's another ridge that's offset. And so you're going to color all the ridges red. It then says color the transforms and fracture zones green. And for our purposes, we're going to mostly just color the transforms. We haven't talked that much about fracture zones, and I don't think they're necessary to put on this map. So these are shown in green. So I've added them as all the offsets in the Mid-Atlantic Ridge, because those are all offsets along transforms. And I've put a few more down here just to emphasize where they're going to go. And the San Andreas Fault, of course, is a transform. But everywhere that these ridges are offset, you're going to find some transforms. And then also the supplemental instruction page specifically tells you which ones I want you to include. It next says, do the convergent zones. And so those are in blue. So again, I haven't done all of them. I'm just giving you a few examples. So I did this convergent zone here. There's one here. There's the Aleutian Trench, which kind of continues over here. There's a few here. But there are others on this map as well. So you want to make sure to put all the convergent zones on there that are listed in the supplemental instructions with labels. Then it says hotspots. So there's just a few hotspots I'm going to ask you to put on. And here's that supplemental instruction page. So these are all the ridges, divergent zones that you need to label, convergent, transforms, and then there's just 5 hotspots here. And I've actually put 3 of them on here for you. I've got Hawaii, Iceland, and Afar. So that's the kind of thing you're going to do, is you're going to choose a color. And if you don't choose orange, or you choose some other colors for these, just put a key right here. Let me know what colors are which. I do prefer that you don't switch blue, green, and red if you have those 3 colors. Okay, so that's the map, and that might take you some time, but that's an important part of this lab. The next 2 pages ask you to kind of look at the map and think about plates and plate boundaries. So we have the western edge of South America. What type of plate boundary is it, if there's a plate boundary at all? And name the plates that meet there. So if we go back to look, there's a convergent plane boundary here along the western margin of South America. And the two plates involved are the Nazca Plate and the South American Plate. So convergent boundary, South American and Nazca Plate. All right, and so you're going to go down and look at these various locations and describe if there's a plate boundary. If not, you're going to put no plate boundary, and you'll put what plate it's sitting on instead of the two plates that are making up either side of the boundary. For this one, you're going to look at these two plate names and figure out what kind of plate boundary is between them. And they want you to be specific if you say convergent, because there's ocean-ocean, ocean-continent, and continent-continent conversions. So I want to make sure that you describe which kind it is. And then what kind of geomorphic feature? Geomorphic means a form on Earth. So is it a trench? Is it a volcano? Is it a ridge? So between North America and Eurasia, we have a divergent plate boundary, and that is indeed the Mid-Atlantic Ridge. And so you're going to go and look at all of these different pairs of plates and the boundary between them. Next, you're going to look at some seafloor isochrons, and we already did the Geol World Lab, so you have some familiarity with this. First, there's just some definitions to answer, and you're going to be looking at this figure right here, which is part of your lab, to answer a lot of these questions. So here it says, what's the age of the seafloor at the North Mid-Atlantic Ridge? In the North Mid-Atlantic Ridge, it's going to be brand new seafloor, right? 0 years old. Brand new. East coast of North America. Okay, so here's North America, here's the East Coast, it's this darker blue, so you're going to put in an age that corresponds to the darker blue. Seafloor around the Hawaiian Islands. Well, it's hard to find Hawaii in here, but it's right there. It's a little bit of a blob that's a little bit lighter color than the surrounding, and that's somewhere in this green zone. So you're going to make estimates. Now it's going to ask you about the Atlantic Ocean. When did it open? Where is the oldest crust found? And you can figure this out, again, by looking at the age of the oldest crust on either side of the ocean. So these questions, I think, are pretty straightforward until you get to number 5. So now it's asking you, what's the average rate of opening of the Atlantic over the past 100 million years? And recall that rate is distance over time. So we used this equation in our last lab. The one problem is trying to estimate where the 100 million year isochron is, which is somewhere in this green area, and then measuring this distance is a bit tricky. So I'm going to help you out. This is from Google Earth, and there's a special program on Google Earth that shows you isochrons of the seafloor, and of course I have that, right? So let's zoom in to the North Atlantic, and I have drawn a line from the 100 million year isochron on the east to the 100 million year isochron on the west, and these numbers are millions of years, and this gives me the map length. The distance of that line is this many kilometers. So you can use that for distance in the Northern Atlantic problem. I've done the same thing in the South Atlantic. Here's my 100 million year marks, and here's the distance given for that one. So you can use that distance, and you can round them to the nearest 100, that's fine. While we're looking at this map, what's going on at the North and South Poles? It's really hard to see on the map that we have. So this is looking down on the South Pole. This is Antarctica. And Antarctica is pretty much surrounded by divergent zones. This Antarctic plate is basically just getting bigger all around. There's spreading going all around it. So that one's pretty easy. The North Pole is a little bit trickier. So here we have the Mid-Atlantic Ridge. It goes up through Iceland, past Greenland, which is here. And then it actually goes just about near the North Pole. The North Pole is right here. And then it goes back down again, right? Because this is the highest point, and it goes back towards the Asian continent. And then we're not really sure what happens there. So when you look on your map, you're going to see this weird looking thing coming down, and that should be colored red. That's actually the edge of this ridge, which of course you can't see because of the projection of the map. But that is that ridge. That's represented by the continuation of the Mid-Atlantic Ridge. So moving on now to the Pacific Ocean, there's a number of questions that ask you about the seafloor patterns of isochrons in the Eastern Pacific. And so here's a little bit better image of those. It's asking you about the offsets between some of these. And so I think this image will be helpful, a little bit better than the one that's in your notebook. Last thing is to look at the Hawaiian Island hotspots and try to figure out the rate that the Pacific plate has been moving over this hotspot. We're going to use the rate equals distance over time equation, and we're going to do it for the Hawaii to Maui islands, and then Maui to Molokai, and then Molokai to Oahu, and then Oahu to Kauai, and then we're going to take the average. So how do we do this? Well, Hawaii to Maui. Okay, so first we need the distance. And that's a little tricky because if the distances were just right here between the closest coastlines, that would be very different than if we took the distance from the farthest coastline. So I'm going to just take a point that starts in the middle of the Hawaiian island, and I'm going to go to this point that says 1.3 million years in Maui because that seems to be a known age, and we're going to assume Hawaii is 0. Now I took that line and I measured it here, and I got about 200 kilometers, so I'm putting that here. Of course, the number of years is 1.3 million years since that hot spot was under here. Now this is today, and so the rate of plate motion is going to be the distance divided by the time, which is 153 kilometers per million year, which means millimeters per year, as you remember, and as is written down here. Let's do the next one, Maui to Molokai. Well, this time I decided to go to the other end of Maui, where it says 0.75 million years, to the point on Molokai where it says 1.9, and I measured that distance. I estimated it at about 120 kilometers using this scale bar. Of course, 1.9 minus 0.75 is 1.15, so that's how much time elapsed between these 2 points when they were each over the hotspot. And then I do my division and I get 104 millimeters a year. So I like to think of centimeters. This is about 15 centimeters. This is about 10 centimeters a year. Both of those are reasonable values for plate motion. But you can see that they're different from each other. So you're going to do the next two, and then you're going to add them up and divide by 4 and see what you get for your average. And that's it. That's our whole lab. Good luck. And don't forget to ask if you have questions.